Hello everyone. In this video we're going to talk about the difference between a resistant and a non-resistant measure, and I will give you examples to illustrate the idea. So before we start, let's understand what are extreme values. These are the values which are very small or very large as compared to the rest of the data values. Such values are called extreme values. These values are also, in a loose sense, are also called outliers, right? Now, what is a resistant measure? A descriptive measure, a measure which is not affected by few extreme values. Mean if you have a data set and in that data set you have some extreme values, then that measure is unaffected. Then such a measure is called a resistant measure. And what is a non-resistant measure? If a descriptive measure is changed by the inclusion of some extreme value, such a measure is called a non-resistant measure. So remember, the mean is affected, which is non-resistant, and median is not, right? How this works, I have to explain this, all these three bullets, with the help of example. So let's go to the blackboard. Here is my blackboard. Let's start. Let's see let's say I have one of the data set. Let's say I have 1, 2, 3, 4, 5, 6, 7, 8, and 9. Let's say I have these values, right? I ask you guys to pause this video and compute the mean. So the mean comes out to be, if you compute the mean, that comes out to be 5. And if you compute the median, it also comes out to be 5. So both mean and the median are the same. Mean is 5 and the median is also 5, right? Now let's see another situation, another scenario. Let us suppose I take another data set, and my data set is 1, 2, 3, 4, 5, 6, 7, 8. Now instead of a 9, I write 99. So look at the difference. Here I have a 9 in the first data set, and here I have a 99. Such a value, this value 99 is called an extreme value. This is an extreme value. Why this is called an extreme value? Because this value is way ahead as compared to the rest of the data values. Now I ask you guys to pause this video and compute, for your practice purpose, compute mean and the median. So in this situation, the mean comes out to be 15, and for your surprise, the median is the same, the 5. The median is the same, but the mean is 15. Now what is the point? What is the point which I want to make? I want to make you to understand this idea. When I include an extreme value, this 99, look at what happens to the mean. The mean is changed from 5 to 15 3 times. It's inflated, what we call it exploded. But what happens to the median? It is unaffected. It doesn't change. So such a measure, such a descriptive measure which is not affected by the inclusion of some extreme values, such a measure is called a resistant measure. So remember, median is a resistant measure. It resists the inclusion of an extreme value, whereas the mean, this is a non-resistant measure. That is the idea I want to tell you, that what happened to the mean and the median if we include, if our data set includes some extreme values. Let us now see the position of mean, median, and mode in the three situations. This is the data set we have. Look at this data set. This distribution. This is like a normal curve. Look at this one. This has a tail to the left side. This is called the left skewed distribution. And this is the right skewed distribution. Now, what is the purpose? I want to show you the position. I want to show you what happened to the mean, median, and mode in the case of these three distributions. Remember, if the distribution is symmetric, like a bell-shaped distribution, and it's symmetric, then all the three, mean, median, and the mode, are the same. They coincide. Look at the mean is equal to median and it's equal to mode. Mean, median, and mode are the same. Now what happened if we have a skewed, left skewed distribution? This is the skewness. Look at that. The tail is on the left side. If the tail is on the left side, the mean is also towards the tail side. Look at that. The mean, this is the mean, and it's also towards the tail. Look at that. This is the right skewed distribution. If the distribution is right skewed, it has tail to the right, and the mean is also towards the tail. So one can understand, one can remember this very easily, that the tail has a tendency to pull the mean towards itself. You can see in this situation. You can see in this situation. Look at that. This is the tail, and this is the mean. The mean, the tail is pulling the mean towards itself. In this situation, the tail is on the right side. The tail is pulling the mean towards itself. So if the distribution is a left skewed, the mean is less than the median, and median is less than the mode. And if the distribution is skewed to the right, the tail is on the right side, the mean is on the right side of the median. And when a number is on the right side, it's a larger number. When a number is on the right side of another number, it means it is a larger number.